Hi and welcome to this video that's going to discuss the area between two curves. This is video 2, topic 1 of Unit 4, Specialist Mathematics. And in this video we are going to reference our math methods work for area between two curves, but we'll be integrating functions that you have learned from your Specialist Maths program. So keep that in mind, and this references work that you'll see in exercise 12b. So recall, and I've said additionally because it flows on from the previous lesson, recall number 4, that the area between curves f of x and g of x for the domain b to a will be the integral between b and a of f of x minus g of x dx. You can go back to math methods to talk about why that is, but in short, it's because if we find the area below f of x, which will be this green shape here, and the area below g of x, that first one, the area below f of x, which will be this orange stuff here, and we do the subtraction, we're left with the orange non-green bit, which is the upper bit, and that's what we're trying to find. So it is the area under f of x minus the area under g of x that will find our area. In this case, x-intercepts do not matter because, as we've discussed, you are actually always finding the area between two curves. It's just sometimes one of the curves is the x-axis, which is y equals 0. X-intercepts do not matter, but points of intersection do matter. So, number 5, if the function f of x and g of x intersect in the domain b to a, you need to be thoughtful about the areas. So you can do something where you split up and decide whether f of x goes first or g of x goes first, as I've kind of done here. So I've got f of x first, but then I've got g of x first in the second one. Or you can be thoughtful and use the method we used earlier and just find the absolute value of both, which will work perfectly fine. And 6, an area enclosed by two functions is bounded completely by them. So if you've got two functions, that they might create one area, or they might create 2, or they might create 5. We wouldn't ask you to do that many in an exam situation, but certainly as you're preparing for the exam, you might get a harder question. So an area enclosed by two functions is bounded completely by them. And 7, do not forget the chickens. As you'll know, my reference to chickens is to do with not forgetting to reread the question and answer the question in full, which is a really common thing for people to forget when they think, and they get carried away and they think they've done the whole question, but they've actually got a little bit more to answer. So let's have a look at example 3. Determine the exact area bounded by the functions f1 of x equals 2x times the square root of 2 minus x squared and f2 of x equals 2x. So we're talking about bounded by, so let's sketch the two functions in our calculator. So go back here, this is one I had up previously, and we're going to sketch function 1, 2x square root of 2 minus x squared equals 2x times the square root. I always put times in it just to make sure it's right. 2 minus x squared. I'll just check I've actually got that right. Yep. And 2x is the other one. So I'll sketch that one, and I'll sketch a second one, which is just 2x. And I'll go up and I'll deselect my one from earlier, and now I'll sketch those two. Okay, so you can see this has worked. We're pretty close, so I can probably drag it down, but that is not working at the moment. I might just exit out of that. Okay, so I can go up this way. So there's our area there. What I need to do is find the 2 points of intersection. I suspect one of them is 0, the other one possibly is 1, but I can go to my gsolve function again, gsolve intersect, and it gives me the first one is at x equals 0, the second one is at indeed at x equals 1. And so I could go through and solve those algebraically in a tech-free exam as well by letting them both equal 0 to calculate those, or letting them equal each other to calculate those values. So now that I've got those two intersection points, I can see the blue one is on top of the red one. That will be my upper function in my calculation. So as I go back, the blue one is of course the first one. So let's go back and do this calculation now. So I need to find the area between 1 and 0 of f1 of x, which is 2x square root 2 minus x squared, minus 2x dx. And so I could do some integration by parts in this question, but I can actually see that the derivative of the inside function here is that function there. And I could play around with this. I could probably do it observationally, but I know that that is a substitution question straight up. So what I'm going to do is take it over here, as I often do, which makes it a little bit easier to set it out. I'm going to write it as 2x, 2 minus x squared dx, and I'm going to let u equal 2 minus x squared. And then do du dx is equal to negative 2x, and therefore dx is equal to du over 2x, but it's negative. Now, this process, hopefully you'll spot, but you look at that, you might think, that's the integration by parts. And if you did integration by parts here, and I'm not going to do it, and let you that u and that be v dash, I suspect you'd also get the same answer and it would work out. So if you do integration by parts, I think it'll take a bit longer, but it's not too bad. I'm going to put this in, integral of 2x, that should have a half above it, my apologies, u to the power of a half, times, instead of dx, I'll put negative du over 2x, and the 2x's cancel, which is great news. I've got a negative though, so this is now equal to negative u to the power of a half du, which of course is equal to negative of u to the power of 3 over 2 over 3 over 2 plus c, but we don't need the plus c because we're going to put it back into a limit-based function. So this is negative 2/3 u to the power of 3 over 2. So now, up here, let's carry on the question. This is now, the integral is negative 2/3 of u to the power of 3 over 2, but u is 2 minus x squared to the power of 3 over 2, minus the integral of this one, which is x squared, between 1 and 0. And so solving that through substitution, I get negative 2/3 of 2 minus 1 squared to the power of 3 over 2 minus 1 squared minus negative 2/3 of 2 minus 0 to the power of 3 over 2 minus 0 squared. That 0 squared is the easy part. And I could just put this straight into my calculator now, but I can see that up here this is negative 2/3 times 1 to the power of 3 over 2, which is just 1, so negative 2/3 minus 1, which is negative 5/3 minus, and down here I get minus a negative, which becomes 2/3 times by the cube root of 8, the square root of 8, and that, oh sorry, that shouldn't be a minus, that should be a plus, gives me, on my calculator, 0.219 units squared. But I could also leave it as 2/3 times 2 root 2 minus 5/3, or better yet, 4 root 2 over 3 minus 5 over 3 would also work perfectly well. So there's the answer to our first example, and we had to do a bit of calculator work, or you might need to do a little bit of work pen on paper to first determine those points of intersection. Example 4, for all a greater than 0, let f of x equal x e a to a of x, so x e to the power of ax, and g of x equal x. Demonstrate that f of x and g of x only intersect at the origin. So to show that they intersect, in A, I want to show that x e a to the x only equals x at 0. The origin is at x equals 0. So I'm going to go through and solve this like normal. I get x e a to the x minus x equals 0. This means that I've got to equal 0, so I can now use the null factor theorem to solve. I'll take x out as a common factor. E a to the x minus 1 is equal to 0. And the null factor theorem says that x equals 0, or e to the power of ax minus 1 equals 0, which means that e to the power of ax equals 1. Now rearranging this function for x, I get, I take a log of both sides, giving me ax equals the natural log of 1, which means that ax equals 0, and because a is greater than 0, the only time this works is when x equals 0, so we only get x equals 0 in both cases. That's A. B. Prove that for x is greater than 0, f of x is greater than g of x in all cases. So there's a few ways we could consider this, but I'm looking to show that x e a to the x is always greater than x, and the x's don't change. So I just want to show that e a to the x is always greater than 1, where a is greater than 0, so a is a positive value. So if a is a positive value, and of course it says here that x is greater than 0, if a and x are positive values, then that means that we've got e to the power of m, where m is greater than 0, because they're both positive values. And e to the power of 0, so the lowest value of m could be, sorry, that should be 0, it should be 1. The lowest value for m is 0, although it can't equal 0. So looking at that boundary, the limit as m goes to 0 of e to the power of m as a decreasing function is equal to 1. And so we've actually got this as a sketch. E to the power of m looks like that, and that is 1. And so if m is positive, it's always above 1, which means that e to the power of ax is always greater than 1, which means that x e to the power of ax is always greater than x. So we can backwards design that. And that should be question B, of course. I've written A. And part C. Hence determine the values for A such that the area between f of x and g of x in the domain 0 to 1 is 1 unit squared. So we've proven here that f of x is greater than g of x. So we're trying to calculate in part C the integral between, and we've got our boundary, 0, x and 1. So 1 and 0 of x e to the ax minus x dx equals 1. And we need to solve this for a. And so, I'll just create a little bit more space for myself. The integrals, the second integral is quite easy, but the first integral you can see there is going to involve integration by parts. So again, we do that separately. What is the integral of x e a of x? Respect to x. Well, I'm going to do my substitutions again. In this case, I'll let my u equal x. Linear is my second preference, but there's no log function. V dash will be the exponential function. And if u is equal to x, then u dash is equal to 1. And if v dash is equal to e a of x, then v is equal to e a of x divided by a. And now I can write out my full expansion. That's equal to uv minus the integral of u dash v dx. So that's equal to uv, which is x e of ax over a, minus the integral of u dash v, which in this case is 1 times e to the ax over a dx. And of course that derives quite nicely, but it's an integration, my apologies. X e ax over a minus e to the ax over a squared. And we've got a plus c, but we don't need it in this case. So I shoot back up here, bringing that result with me, and it means that I've got x e to the ax over a minus e to the ax over a squared minus a half x squared between 1 and 0 has to equal 1. We substitute in our 1 and 0 now, and I'll need a little bit of space for this, but I get e to the a over a minus e to the a over a squared minus a half, and I'll subtract from that what happens when I substitute in 0, which actually turns out to be 0 minus e to the 0 over a squared. That's the only one that doesn't disappear, minus 0. We need that to equal 1, and so I get, I've got some common denominators. I know I've got a's in a few different places, so I'm going to have to be very careful with this. E to the a over a minus e to the a over a squared plus 1 over a squared minus a half equals 1. I've just done some rearranging. I'm going to multiply everything by a squared to make it a bit nicer before I probably go to my graphic calculator to solve. So I've got a e to the a minus e to the a plus 1 minus a squared over 2 is equal to a squared, and I can make that slightly nicer again. A e to the a minus e to the a plus 1 equals 3a squared over 2. And now I just need to solve that on my graphics calculator, if I remember it. So we exit out of there, and I'm going to go to my main menu and my run screen. In here I'm going to go into my options, calculate, solve numerically, and it was a, which I'm using as x, e to the a minus, so I'm going to have to reference this again, e to the a plus 1, e to the a plus 1, that's not what I meant to do, shift equals, and it was 3a squared over 2, and I'm going to solve that for a, close brackets, and let's see what comes out. So multiple answers may exist, but I do get these two answers, 0 and 1.5547, and so the answer in this case will be a is equal to 1.5547. So there you have it. The solution to the second one, which is quite an involved question, complex familiar or complex unfamiliar. All the best.